or the big structural hub. So this is a place where you learn, build, and innovate. So today I want to tackle a question from past paper, that is KNEC Structure 1, July 2015. The question is number 3 and it carries 20 marks. So the question reads, Figure 4 shows the shear force diagram for a simply supported beam. Question number 1, sketch the loaded beam indicating the supports. Question number 2, calculate the bending moment at every 2-meter interval. Question number 3, sketch the bending moment indicating the critical values. So this is the beam. As you can see, a beam with a shear force diagram. So the first thing to note while drawing a shear force diagram, when you draw a diagonal line like this one, it indicates this is a UDL on that section. So from here to here, a beam is loaded with a uniform distributed load. And from here, again, we have a point load loaded at this point. So from here to here, a beam is again loaded with a UDL because a line, this is a diagonal line joining 2 points from here to here. Then from here going upward, we'll have a reaction. So as you have been told, it is a simply supported beam. So for a simply supported beam, it only have 2 supports. And if we can label this diagram as A, as A, B, C, D, like that. So it means at A, we'll have a reaction. Why? Because this is a baseline, and from baseline going upward is positive. So it means here we have a reaction of magnitude 12.4 kilonewton. So here we have a reaction So that is a reaction. Again, we have another reaction at C. So we have 2 reactions, reaction at A, reaction at C. Again, another thing to note, at this point, from here to here, We have IODL. We have IODL. IODL, let's say X kilonewton per meter. Again, at B, we have a point load. Let's call it Y kilonewton. Again, from here to here, we have IODL because you can see a diagonal line joining the 2 points. So we will have IODL, let's say Z kilonewton per meter. Again, at D, we have a point load. Let's call it M. M kilonewton. Why are we giving it or putting here a point load? Because if you take 13.6, it is negative, plus reaction at this point, it will bring you somewhere there. Then it will maintain constant up to this point. Up to this point, if you take this point load, you subtract M kilonewton, it is supposed to bring you back to 0. 0 kilonewton. So after having or after naming our diagram like that, we can comfortably start calculating the loading on the beam. So let's begin. So we have our B with reaction at A, which is a support, and a UDL of X kilonewton per meter from A to B, and then again at B we have a loading of Y kilonewton. So this is a point load or a concentrated load. And then from B to C we have a UDL of Z kilonewton per meter. And then from at D we have M kilonewton as a point load. So from here to here is overhanging. And then we have another reaction at C. So now we have identified our reaction. So our reaction and our support. We have support A, which is a reaction, and support C as a reaction. So let's begin calculating the value of X, Y, Z, and M. So we know that if we start calculating the shear force from point A, it means from here to here is positive. So take 12.4. Then subtract from this a loading from here to here, of which we have a UDL of X. So this X, you multiply first by distance to change it to a point load. So distance is from here to here, so times 4. Like that. Again, so by doing this, it should give you 6.4. So equals to 6.4. So 12.4 minus 4x should give you 6.4. So when this, if you cross, when this crosses to the other side, changes from positive to negative, and this one, and this one, it will change to a negative. So 4x should give you 12.4 minus 6.4. So 4x should give you 6. Divide both sides by 4 by 4, which imply x equals to 1.5 kilonewton per meter. So now we have a loading at this section from here to here. Our loading is 1.5 kilonewton per meter. And then again, shear force at B. At B, we have a loading which is a point load downward on the beam. So a loading is Y. Again, if you take 6.4 and then you minus Y, it should give you this minus 1.6, like that. So because below the baseline is negative, that's why I have used minus 6. So 6.4 plus 1.6 should give you Y, which imply Y equals to 8 kilonewton, like that. Again, we have a UDL from here to here. So you take negative 1.6 minus this UDL, it's Z, times the distance, because you are changing this UDL to a point load. It should give you negative 13.6. It should give you this. So negative 1.6 minus 6Z should give you 13.6 negative. So negative 6Z should give you negative 13.6 plus 1.6. So which imply Z equals to, take your calculator, so Z is equal to 2 kilonewton per meter. Like that. Again, now we are at this point. As you can see, if we take 13.6 plus C, which is a reaction at C, so we don't know the value of this C, but it should give you 4 kilonewton. So take negative 13.6 plus reaction at C, it should give you 4 kilonewton. So it means C equals to 4 plus 13.6. So this one will give you 17.6 kilonewton. So our RC is 17.6 kilonewton. Now we are at RC. We want to find the loading at D. Loading at D now we already have 4 kilonewton here. So we already have so the next thing to do is to determine the loading at D, M, kilonewton. So if you take this m, this 4, so if you take 4 minus m, it should give you 0, because at this point, if you subtract this one, which is from here to here, it is supposed to bring you back to 0. So, which imply m equals to 4 kilonewton. Now, we have calculated our loading on the beam. We have reaction at A, which has a 12.4 kilonewton, and then a UDL from A to B of 1.5 kilonewton per meter, and then at B we have a concentrated load or a UDL of 8 kilonewton, and then from B to C we have a UDL of 2 kilonewton per meter, and then at RC is a reaction at C, we have 17.6 kilonewton, and then at D we have 4 kilonewton. Now we can draw our beam, indicating the loading and their respective spanning. So let me wrap. So that is our beam. Loaded with these values. So we have from point A to B. A to B we have 1.5 kilonewton per meter, 1.5 kilonewton per meter. And then at D we have 8 kilonewton, 8 kilonewton there. Then from D to B 2 kilonewton from here to here. And then at C we have 4 kilonewton. So by doing so, you have now calculated or determined what the question. From there now you have calculated or you have solved equation. From there now you have solved equation number 1. So let's go to this is number 1. Number 2, determine the moment at a 2-meter interval. So moment at every 2 meters interval. So before I begin calculating the moment at every 2-meter interval. And let me extend this line. Like that. So, for you to calculate moment at every 2-meter interval, you can use two methods. You can first draw the shear force diagram and start calculating areas for the shape uh, resulted from the shear force diagram. For you to calculate moments at every 2-meter interval, you can use two methods. The first one is to draw the shear force diagram. After drawing the shear force diagram, you will now start calculating the areas from the figures you have drawn. And then number two, you can calculate moment direct by using force times perpendicular distance. So, because the question never requested us to draw the shear force diagram, we will go direct to the moment at every 2-meter interval. So, if I can say, or I can split this span into 2-meter interval like that, then here we have so this is 2 meters, 2 meters, 2 meters, 2 meters, 2 meters, 2 meters, like that. So we want now to calculate moment at every from here, then here, then here, then here, then here, and there. So let's begin by saying bending moment at A will be 0, which is equal to bending moment at C. So at C is 0 and at A is 0. So let's call this point, let's label as A, B. Let me use another pen. So this is A, B, then C, then D, E, F. So bending more, that is it. You go to the next point. Bending moment at small a. So bending moment at A. You know that bending moment is the force times perpendicular distance. So to calculate the bending moment at A, you will consider the reaction, which is A, and also a UDL of 1.5 kilonewton per meter. So bending moment at A, in which direction is reaction A moving in reference to point A? It is moving in clockwise direction. So that one will be RA, which is 12.4 times 2, the distance, and then a UDL of 1.5 kilonewton. So from here to here, so it's moving in anti-clockwise direction. So minus 1.5 times 2 times 2 over 1. So that one will give you 21.8. Bending moment at B. Bending moment at B. We are now at this point. Now, let's see. So it will be RA in which direction? A reference to point B. So that is clockwise. So that one will be 12.4 times 4. Again, we have a UDL spanning at 4 meters. In which direction is a UDL moving? So it's begin here and it ends here. So that is anti-clockwise. Minus 1.5 times 4 times 4 over 2. So that one will give you, take your calculator and punch and give me your answer. So we have 37.6. Bending moment C. So bending moment at C, we are at C. So we have a reaction RA moving in clockwise direction. So that is 12.4 times the distance. 2 plus 2 plus 2, that is 6. And then we have this. This UDL of 2 kilonewton per meter. In which direction is that UDL moving? This way, minus. So minus 2, and it is spanning 2 meters from here to here is 2. So you convert to a point load times 2. Then the moment it acts at the center over 2, we come to this 8 kilonewton, which is a concentrated load or a point load. So it will be 8 times. In which direction is this moving? Again, anti, so it's minus 8 times the distance is 2 times 2. We have again a UDL of 1.5 spanning at 2, at 4, not 2, at 4 meters. So in which direction is that moving? It's moving this direction. So that is anti-clockwise, minus 1.5 times 4 times 4 over 2 plus 2. So this UDL of 1.5, we first convert to a point load by multiplying the distance. So 2 plus 2, that is 4. And then the bending moment acts at the center. So the center is 4 over 2. Then you add 2 because our point of reference is C. So this one, bending moment at D. So the bending moment at D will be, we are at this point, D. So it will be the bending moment, it will be RA moving in clockwise direction times the distance, so that is 12.4 times the distance, 2 plus 2 plus 2 plus 2, so that is 8 times 8. And then we have a UDL of 2 kilonewton per meter. So moving in anti-clockwise direction, so minus 2 times the distance covered is from here to here. So that is 4 times 4 times 4 over 2. And then we have a point load of 8 kilonewton moving in anti-clockwise direction, minus 8 times 4. The distance is 4 minus 1.5. Again, UDL of 1.5 moving in anti-clockwise direction times 4. You are converting to a point load, then times, that is 4 over 2 plus from here to here plus 4. Kilonewton meter. So bending moment at E will be reaction at A, which is moving in clockwise direction, so that is 12.4 times the distance is 10, and then we have a UDL of 2 kilonewton per meter moving in anti-clockwise, so minus 2 times, you have these two from here to here, 2 times 6 times 6 over 2. Then we have a point load of 8 kilonewton moving in anti-clockwise direction, so minus 8 times 6. Again, we have a UDL of 1.5 moving in anti-clockwise direction, minus 1.5 times 4 times 4 over 2 plus 2 plus 2 plus 2, that is 6. Then you get the answer. After doing so, now you can draw the bending moment diagram as guided on the question paper Roman number 3. Again, something to note down. Some of you may be asking themselves, why did I not use the shear force diagram to calculate the bending moment at this respective point? So it is because I didn't draw the shear force diagram. So this is another way of calculating the bending moment at respective points. And the question did not ask to draw a shear force diagram because the question itself had a shear force diagram. So it was a reverse question. So there was no need to draw again a shear force diagram. So I just went direct to the bending moment values. So now we can draw our bending moment diagram. So let me use another pen. So this is the baseline. So bending moment diagram. So at point A is 0. At point small a is 21. So here you have 21. So 21.8. Done. At B is 37. At B you have 37. At B 37.6. So done. At C you have 30. At C you have 30.4. So done. At D we have 15. At D we have 15. 15.2. Then at E we have negative 8. So at E, negative 8. Done. So we just from here is a smooth curve because it's a UDL. Again a curve again, a curve again, a curve again, and then a diagonal line. So this is plus, this is minus. Like that. And the question ends there. You have your 20 marks. So let's meet again in my second or my next session. So you can share, you can comment, you can like, and recommend your fellow students and your fellow lecturers to this wonderful YouTube channel or David Structural Hub.